Yo, so I'm back uh on part one of derivatives. I went more of the bigger picture. This time I'm going to be focusing more on the graph. So over here on the left side of the screen, I have the equation for a secant and the equation for a derivative. M tan or dy over dx. Both of these are the same thing. M just means slope of the tangent, and the derivative is the slope of the tangent. The only real difference between these two is that the slope of the tangent is as the limit of h approaching zero, but most of it is just the same as the secant equation, so pretty easy to understand. I'm gonna draw the unit circle again, just to give it a little refresher on the correspondence between secants and derivatives. I'm going to do secants in blue and derivatives in purple. So let's start off by drawing our derivative first. So again, derivative, it only touches at one point. So that only touches at one point on our circle, and that's here. We just can call that point A. Point A, right? And a secant, the definition of a secant is any line that crosses the circle twice. So that crosses here and here, right? And a secant, we can use rise over run because it has 2 points. A tangent, we cannot use rise over run because it only has 1 point. And so we have a secant there. Let's just say we have another secant here. Another one here, another one here, another one here, another one here, another one there. You see how the lengths of the secants kind of funnel towards, like they get shorter and shorter, kind of make that it. Let me draw another representation of it. It's kind of like that, and then you eventually get to your derivative, right? The length of the secants gets smaller as you're approaching your derivative. This is a visual representation of your limit. And this is how I like to think of it. And we can even give each of these blue lines a value. Like this one could be 1, this one can be 0.5. Of course, it's not drawn to scale. This can be 0.4, 0.1, and like this very last one can be 0.000001. And it'll have an infinite number of dots between this purple dot and the blue one above it, just because it goes on forever. And over here on our axes, we have x and y. And so we're going to have our secant can be any 2 points. So we're going to have a secant here and a secant up here. And let's just say our tangent, the line that touches, the tangent, the point of finding the tangent is because we want to find the slope between this given area, right? And it, like if you were to do it algebraically, you would do rise over run, which would mean you would do x1 over, or y1 minus y2 minus y1 over x2 minus x1. But I'm going to show why that's not really an accurate representation and why it doesn't really work for this scenario. Right, so we have your point set up. And I covered this over the last in the last video. Go watch that if you need to. But our secant is gonna our derivative. Let me just make it right there. Right, it's point A. Now the slope of our secant, you can do the formula. If you do to find the slope of the secant, it's this formula right here. And a visual representation of the slope would be something like that. like that. Good enough. And you can see how I'm within the ballpark of finding the slope of this point. Like it's close, but it's not exactly there. That's why the my bad. We good. We're good. That's why. So like I was saying, the slope right here. Another way another way of writing m sec is average velocity. Another way of writing m tan is instantaneous velocity, because your tangent or the slope of your tangent gets you the slope at an instant point, like at one single point, at that instant, and your secant will give you the slope over like a multitude of points, the average. So the blue line is the average slope of this red line here. Another visual representation. The whole thing's about visually representing a derivative. Now, the example that I was using here, where my cursor's over. You see how the secant lines funnel towards the derivative. So if we were going to have secants that do that and that and that and that, or let me get a finer point. There we go. A secant there and a secant there. You can see how the space between the secants gets smaller. And what do we call that space? We call it h. So we can just call this h1, which is the space between our original points. And we can give those points values also. We can call this point B and C. So h1 is the distance between point B and C. This point can be E and F, and that would be h2. h2. And each one of these secant lines would have an h, but let's just skip to the closest one to the derivative that I have represented. These will get infinitely closer to the derivative, but we can just call this point G and H. Or let's not use H. G and whatever.
Where'd you take my?
And we have G and Q. Now the distance between those 2 points, we can just call H3. Now you see how the distance between the 2 points is getting closer and closer? That's another way of representing as h approaches 0, because like we can even get the distance between the 2 values like numerical numbers. So this can be a value of 2. We can even 2 feet. This can be 0.5 feet, and this can be 0.0001 feet. You see how the values are getting closer and closer? That's because your h, the distance between your 2 points, is approaching 0. And I hope that helped you understand why h approaches 0 and the relationship between a secant line and a tangent line, and that's all.